We are live.
Okay, good. Hello, everybody. Welcome to the reinforcement learning session. And today we have a great speaker, Professor Doina Precup, who is an associate professor at the McGill University, as well as a core member at MILA. He also leads the DeepMind Montreal lab. And her research interests are in the areas of reinforcement learning, deep learning, time series analysis, and many other related topics. She became a senior member of the Association for Advancement of Artificial Intelligence in 2015, Canada Research Chair in Machine Learning in 2016, and Senior Fellow of the Canadian Institute for Advanced Research in 2017. And I also want to mention that I met Doina in her hometown a couple of years ago, right? So she's also hosting a machine learning summer school there, and I was really impressed by the hospitality and the great food I had there. So good to host you here in Tübingen. Welcome to Tübingen virtually, Doina, and the stage is yours.
Thank you very much, and it's really a great pleasure to be here. And I wish I were here in person in Tübingen. I'm sure it would have been a great time, but we do our best in these strange times. And so I will talk about reinforcement learning today, and I think you've already had a preview of this topic with the lecture from Peter Dayan, who talked about reinforcement learning in the brain, but really a lot of that, in fact, was reinforcement learning. So you might have some deja vu as I'm showing you various algorithms on the slides, but I hope that the more perhaps computational and theoretical perspective that we see today will complement nicely what he would have told you. Today, I'm going to focus on a category of reinforcement learning methods that are with the purpose of prediction. They're value-based and model-free. And if we have time, we're also going to talk about control, not just prediction, including DQN, but always focusing on methods that estimate how good a state in the environment of an agent is. And tomorrow we will talk more about policy gradient methods, as well as some of the more advanced topics, a little bit more on exploration and more on temporal abstraction as well. And I want to say that a lot of the material in this talk is based on the book by Rich Sutton and Andy Bartow. Also, I'm quite grateful to my collaborators, both at McGill and Mila, as well as at DeepMind, for feedback and just for being continually awesome colleagues. So you've seen a lot of supervised learning. Supervised learning is about learning from input-output pairs, how to make predictions where we have labels, so we have ground truth. And this is, of course, great in many practical applications, but at the same time, this is limiting in the sense that we now need to have a teacher that provides us labels. You've also talked about unsupervised learning. So unsupervised learning is just about having some data and trying to find some structure in that data. You know, maybe we have some trajectories from an accelerometer. These look like periodic trajectories. There's, you know, maybe one of them is smooth and the other one is not. But an agent that's faced with just a bunch of data without any guidance on what is interesting might find it quite challenging, actually, to deal with this and to decide you know, what it should focus on. So reinforcement learning to me is in a sweet spot in between these two things, where we do have feedback from the environment, so it's not as unruly as unsupervised learning, but this feedback is coming in the form of rewards rather than in the form of actual labels. And really, a lot of the ideas that I talk about are, in fact, inspired from biological learning, animal learning theory. So in one of the pictures, you see this little mouse who has to press some sequence of levers in order to get some food pellets. And of course, this is at the root of classical conditioning, instrumental conditioning, and other such theories in animal learning theory. In computational reinforcement learning, we have a very similar setup. We have an agent that's embedded in an environment. And this agent is going to perceive something about the environment, get some observations. it will be allowed to take actions in the environment. And as a side effect of these actions, the environment will transition to a next state, and it will also receive a reward. And so
Can I interrupt
I'm not sure
you?
if my slides are still showing.
Your slides are not showing, actually.
I'm trying to figure out what that is. Hold on. And resume. It's okay? So this agent is going to have to learn by trial and error. It's going to take actions in the environment. It's never really told what's the right action to do, but it has to try things out and gets the reward feedback. And from this feedback, it will, over time, understand which actions are leading to positive outcomes, and the probability of those actions will be increased. The other interesting aspect of this problem is that the reward is often delayed. So the agent does not know right away if an action led to a positive outcome. This might only be visible quite a bit later. And so here's one example of this paradigm, which is adopted in systems like AlphaGo and AlphaZero. So in this case, we have an agent that is trying to play a game. It's the game of Go. It's a two-player perfect information game, but it is why is the sharing not working? Can you see my slides?
It didn't change, actually. It's still the slide with the mouse.
Okay. I am not. Just give me 1 second, please, to try and figure out why this is not working. I think the sharing just drops automatically for some reason. Okay, let's try to play again. Okay. Okay. So, no, this is not going to work. Can you see my slides when they are in this view?
Yes, if there's no need to be full screen, maybe we can go like that. Otherwise, Keynote sometimes, it has a conflict with Zoom. I don't know.
Yeah, I will try to go like this, and hopefully that fixes the problem.
This works fine. Okay.
Okay. Okay. So in this case, we have an agent that's looking at the board of the game, and so the perception is the state of the board. We can think of this as an image, and the agent has an action space. It has a set of legal moves that it's allowed to take, and the reward only happens at the end of the game. At the end of the game, the agent is going to win or lose. And so if it wins, it gets a reward of +1. And if it loses, it gets a reward of -1. And otherwise, there is no feedback during the game. So in some sense, you can realize that this is a very hard problem because there is a big number of time steps that's going to elapse between when the agent made, let's say, a really good or bad decision and when the outcome is observed. And so at the core of a lot of reinforcement learning algorithms is going to be this problem, which we call temporal credit assignment. How to decide when the reward happens, which of the previous time steps, which of the previous states and actions are really responsible for this reward. Now, why would we take this approach, which seems very low on information, compared to, let's say, the supervised learning approach? So let's consider the supervised learning approach. In that case, you would have an expert that looks over the agent's shoulders and at every board position might suggest to the agent what is the right move to take. So that is obviously great information, but now we need an expert And not only that, we need the expert to label sufficient amount of data for us that we'll be able to understand the dynamics of the game and what makes for a good board position. Now, of course, we can do this maybe for 10,000 games, 30,000 games, but at some point there is a limit to how much supervised data we would have, whereas an agent that can just experiment with the game and play the game can potentially get significantly more data. And in this particular case, Go is a game that we can easily simulate. And the agent can essentially clone itself and play games against itself, sitting in a corner. And so getting the experience actually in this case is quite easy for us. The other interesting aspect of this idea is that because the agent is experimenting and trying new things, it can possibly discover ways of playing which are superior to anything that a human perhaps knows. And this is indeed something that we observe in AlphaGo, and it has been observed in several applications of reinforcement learning that these agents, because they train by themselves and experiment with the environment, can possibly achieve superhuman performance. Now, what's inside the head of this agent? This is what we're going to look at during these two lectures. There are two kinds of knowledge that the agent needs to have. One of them, which is embodied in this network here, is the policy. The policy says how we're going to act. And so in this case, the policy is going to give us a probability distribution over different places on the board where the agent may want to play a piece. The other quantity that is going to be very helpful is the value function. And so this is sort of depicted here in our case, because we have to do with images. This is represented as a convolutional network. The value function is trying to estimate the probability of the agent winning from the current position. And so the value function is an artifact that's going to help us in the search for a good policy. Its goal is going to be to help the agent understand which of the actions are leading to outcomes that are better than the current situation. And so when the agent is trying to control the environment, it's going to try and increase the probability of actions that are leading to outcomes that are better than expected. Now, what are some key features of reinforcement learning algorithms? Again, this is trial and error search. The agent takes actions without being told what to do and trains from all of the data that's being obtained. What this means is that basically oftentimes the agent has to train in simulation because we want it to be safe and not damage anything. It can deal with stochastic environments. So in the case of Go, the agent can play against different opponents. Those opponents will have different ways of playing. So that can be viewed as randomness in the environment. We have delayed rewards. So the agent in particular may need to make short-term sacrifices in order to obtain some long-term gains. Not unlike students who go to graduate school, perhaps doing some short-term sacrificing in order for perhaps longer-term career gains. And then the learner has to balance the need to try new things and the need to exploit its knowledge. So for example, if we have a Go player, it would like to try and understand what is a good way of choosing actions. So it has to try many actions, that's exploration. But at the same time, it also wants to win games. And so that means exploiting its current knowledge. And so that's actually quite a hard trade-off. We'll talk a bit today about it, but we'll talk also more about it tomorrow. Reinforcement learning as a field has developed at the intersection of many different fields of inquiry, among them, of course, machine learning and AI, but also cognitive science and neuroscience, economics, ideas from bounded rationality, so agents that don't have unlimited capacity to reason come into play at times, and then also optimal control and operations research, which talk a lot about this idea of choosing actions. One of the very early successes of reinforcement learning was this program called TD-Gammon. This is a backgammon player that was developed by Jerry Tesaro at IBM in the 1990s. And in this case, we have an agent that is learning to play backgammon. Again, this is a two-player perfect information game, but it's a stochastic game because there are dice rolls. So even if you play against the same opponent, the dice rolls actually bring an element of randomness, and also they increase the dimensionality of the space. And so the approach here was to take a neural network. At the time, we didn't have deep networks, we had two-layer networks. And so this is a two-layer network that is looking at the state of the board and is trying to estimate the probability of winning given the current state. And of course, then the agent can also do a little bit of search. So from the current position, it can consider all of its possible actions and see what the outcome of those would be. And from those places, it can decide what's the probability of winning and just follow the path that leads to a high probability of winning. And even at the time, this player, which trained against itself, quickly became really good. And in fact, it became the best backgammon player in the world and played against the world human champion at the time and won quite handily. An interesting aspect was that originally Jared used a lot of expert handcrafted features for this program. But later on, this was kind of discarded in favor of a more pure data-driven approach, where you have a neural net. Reinforcement learning is essentially providing the error function for this neural network, and this error gets backpropagated, and the representation and the policy are both learned as a side effect. And that approach actually led to much better performance than using expert features. It also led to much better performance than doing supervised learning. And this is partly because the agent, by playing against itself, was able to generate much larger quantities of data than what would have been possible for a supervised learning agent. Okay. Now, over time, of course, there have been many more applications of reinforcement learning, not only in games, but also in control tasks like helicopter control, robotic control. Reinforcement learning is quite widely used in A/B testing, right? So in recommendation systems where maybe the system is trying to understand what to show you next. And I'm going to show you a few more of these examples. In all of these cases, the performance was better than what could be obtained by other methods. And so that's what has really driven the motivation for this line of research. The modern interest in reinforcement learning has been partly driven by the work at DeepMind on Atari games. And so Atari is this gaming console that was alive back in the 80s. And now, of course, we have emulators and simulators. And so there is a set of 57 games, and these agents were trained on these games. And in fact, over time, these agents have become better and better. And the most recent incarnation, which is called Agent 57, has in fact superhuman performance in all of these games. So in these cases, we have agents that have the same brain, right? So the same structure of a neural network, the same learning algorithm. They just train with different data that's obtained from these games. So another very early example, these are some little robots from a robotics lab in Japan in the 90s. This is a little robot that's trying to crawl, and at the beginning of learning, of course, it doesn't know how to do much of anything. And it can be trained by reinforcement learning. In this case, the state space of the robot has to do with the positions and velocities of its joints. The action space is given by actuation at these joints. And so both the state space as well as the action space are continuous. And the reward function has to do with progress against the desired direction. So in this case, we're trying to get the robot to move in the direction of the arrow. And so the robot is rewarded for making horizontal progress in the direction of this arrow. Now, at the beginning, as you saw, the robot is quite incompetent. After learning, it can learn how to use its body, which is quite a simple body, in order to crawl in the right direction. Now, we can also teach the robot to crawl in some other direction, okay, like crawling backward. Of course, this robot is not particularly good as a dynamical system. at crawling backwards, but it's doing the best it can. It's learned a different policy, a different way of behaving, because the reward is different. And then, of course, we can take the same idea, the same algorithm, and just put it in on a robot that has a different body, right? So here's a robot that is actuated in terms of segments, and this robot can also learn how to crawl using the same approach, the same algorithm, right? But now, of course, the policy is adopted to its body. So this gives you a sense that these algorithms are actually quite flexible in terms of the kinds of tasks that they can do. Now, there's also a question of, is reinforcement learning good for other things other than games and robots? And this is one application here that was done years ago in our lab by my colleague Joel Pinot and several of our students and postdocs, which is applying reinforcement learning in a medical context for epileptic seizure control. So in this kind of application, you have patients that have bad epilepsy, and so their seizures cannot be controlled by medication. And instead what happens is they get a little implant in their brain that's essentially like a pacemaker that stimulates the brain at a fixed frequency. And of course, we don't really know in the long run what happens if we do this kind of fixed frequency stimulation. So ideally you do as little stimulation as possible, right? The role of the stimulation is just to break up seizures when they happen. So if you could do closed loop control where you actually know when a seizure would happen and only stimulate them, that would be ideal. Right? And so we've explored reinforcement learning for this problem. In this case, the sensory information for the reinforcement learning agent has to do with brain activity and the electric patterns of brain activity. And whenever you have these implants, they also do sensing. And so we have some of that information. Obviously, it's quite noisy. And then the actions are these stimulation pulses. And because it's hard really to stimulate by pulse by pulse, really the agent is choosing a frequency of stimulation. And then the reward actually has two aspects to it. On one hand, we would like to minimize seizures, but on the other hand, we don't want to stimulate too much. And so this is actually quite an interesting case from a practical point of view, where oftentimes we will have some trade-offs, right? The reward is not as easy to see as in a game, but there may be a trade-off between different considerations or different factors. And so, in fact, when we run an algorithm, we may explore this trade-off. And so the little colored bars here that you see are essentially results that are obtained for different trade-offs of these two different reward functions. A similar kind of application, but more in the continuous control, sort of classical control domain, is in the picture below. This is an application that we did in collaboration with Hydro-Quebec, which is a company in Quebec that runs power plants. And so the idea here is that you want to have a reinforcement learning agent that decides how much water it should turbine. So should it open the dam more or less? And of course, this is maybe in most cases a decision that is easy to make even by heuristics. But there are situations where this is actually a hard decision to make. For example, if the amount of precipitation is unusually high because we have climate change, right? Maybe the snowfall was too high. Sometimes we have ecological constraints, so there may be fish in the river. The fish need to spawn at those times. We just want to keep the water levels very steady. And so on one hand, we want to sort of maximize profit, but on the other hand, we have all these other constraints that we're trying to satisfy, not flooding and keeping the ecosystem happy and so on. And so a reinforcement learning agent can actually be trained based on historical data, especially historical weather data, in order to try and carry out this hard optimization problem. Now, in this case, it's a typical example actually where it's very hard to estimate value functions, but it's much easier to work in policy space because the space of policies is actually pretty simple. You open and you close valves, right? And so this was one application where a policy-based approaches actually turned out to be very useful. And so, so this is, I hope, just to give you a sort of a taste for why we're interested in reinforcement learning I will now start talking a little bit about the computational framework of reinforcement learning and sort of the setup of the problems, and then I'm going to take a little break and ask for some questions. So the computational framework that we work with is that we have the agent embedded in the environment. It perceives the state of the environment. And we're going to consider a case where the time is discrete. So there's a clock that ticks. On the clock tick, the agent looks at the state. It's going to take an action. One time step later, the agent will observe the reward, which is a number, and it's going to observe the next state of the environment. And so the goal of the agent is to maximize the long-term expected return. And so this is a quantity that we're going to have to define. And so the agent is looking for a policy, a way of choosing actions that is essentially as good as possible. Now, we're going to introduce just a little bit of notation. So we're going to call S the state of the environment. And you can think of that as any kind of relevant information, observations that the agent is getting. R is the reward that the agent is getting, and A is the action. And so the agent is going to interact with the environment on these time ticks. And on the bottom picture, you see a trajectory. So a trajectory means the agent is starting in some state, maybe initialized at random, or maybe it's a fixed starting state. It goes through a sequence of actions, it receives the rewards, and possibly eventually enters a terminal state, right? So that's the case of a game where at the end you enter a state where the game was won or lost. And so now we have an episode that's terminated, the agent restarts and goes all over again. And so the data that the agent perceives is in the form of these trajectories: state, action, reward, next state, next action, next reward, and so on. So off the bat, two observations, okay? One is that the data typically is not IID, right? Unlike in supervised learning, where often for convenience, we make IID assumptions. In this case, the data is definitely not IID because the next state we observe is correlated. So it's oftentimes a direct effect of what the agent did at the previous time step. Not only is the data correlated, but the data is really a result of the agent's actions. And so the agent needs to have a policy that is interesting enough that it can lead an interesting life and observe rewards. And so that's going to be sort of part of the challenge here. So again, just contrasting a little bit supervised learning versus reinforcement learning. In supervised learning, typically you have inputs and outputs, and you have an error signal that comes here that compares a desired or target output to the actual output that's being produced. And this error is going to drive the update of parameters that are in this box. And this box really can be any kind of function approximator. It could be linear or a neural net or any kind of gadget that you want to put in there that has a set of parameters. In reinforcement learning, the desired outputs are actions, right? So really the box that we're interested in is a mapping from inputs, that is states, to actions. And the training information comes in terms of rewards and penalties. So even though we want actions at the output, we don't compare the action that the agent took with the target action that it should have taken. We take the rewards and we have to construct out of them a loss function or an evaluation that the agent can then learn to use to drive the action choices. And so our objective is going to be for the agent to get as much total reward as possible. And so if we are looking now at the agent's learning task, the agent's learning task is going to be to obtain a policy. And oftentimes we think of this policy as being stochastic. That means the policy is defined as a probability distribution of actions conditioned on the agent's state. And of course, we can make this deterministic if we want, right? In which case, the input is going to be a state and the output is going to be an action. But we actually never have examples in the form of state and desired action. Again, the examples are coming in the form of these trajectories with rewards. And we need to figure out how to change the policy in response to these rewards. So all RL methods that we talk about specify how the agent should change its policy as a function of the rewards received over time. Now, in order to drive this process, the agent needs to understand its long-term returns, right? So because rewards are sparse, because the reward is often delayed, we don't want to focus on the immediate future, we want to focus on the long-term future. And so if we have a sequence of rewards, RT+1, RT+2, and so on, the agent would like to maximize the expected return, which is some cumulative measure of these rewards. And there's different ways to define these cumulative measures. One way is just to look at the total reward, so the sum of all future rewards in the episode. The other one is to look at discounted reward. This is a formulation that we're going to look at actually a lot. In this case, essentially, the agent prefers to get a reward sooner than later, and so future rewards will be discounted by a factor. And then there can also be a formulation called average reward. So average reward means that we look at the sum of rewards over time, but we always divide by the amount of time, and the more reward per time step you get, the better. It's an interesting formulation from a theoretical point of view. It's perhaps a little bit less used in practical applications for some difficulties that we won't really have time to get into. So let's say that we have an episodic task. So the task for sure ends, okay? It's like playing a game, or there's trips to a maze or something like this. Now we can use just the sum of rewards that the agent receives to tell us what is a good long-term outcome. And so here's a very simple task. This is called mountain car, very toy example. You have a little car here that's trying to get at the top of this hill as quickly as possible, but the car engine is weak, okay? And so the policy that just goes forward towards the top of the hill is just not going to make it because the car does not have enough energy. And so instead, an optimal policy needs to kind of pump energy. So it needs to move the car using the back slope here, sort of pump the energy of the car. And this is an idealized system, so there's no friction, right? Just need to pump the energy of the car until we can really make it to the top of the hill. So the reason this became a sort of a famous or canonical problem in reinforcement learning is that it's a typical case where an agent needs to learn that just greedily going towards the goal does not lead to success. And instead, it needs to learn this more complicated thing that you need to move away from the goal in order to really be able to make it in the future, right? So there's this kind of long-term view that the agent needs to have. Okay, so how do we model this as an episodic reinforcement learning problem? Well, one way to do it is simply to penalize the agent for every time step during which it is not at the top of the hill. Okay, so every time step that elapses, you're not at the top of the hill yet, you just get a -1 penalty. And so the return of the agent is just going to be the total number of time steps that it spends before reaching the top of the hill. And the return is going to be maximized if we take as few steps as possible. Okay? And in terms of the state space and the action space, in this particular case, the state space is continuous. We're interested in the position and velocity of the car, right? And the action space is discrete. We can accelerate forward or we can accelerate back. And so the action space is quite simple. The state space is continuous, so maybe that's a little bit of a complication. Now, whenever I teach reinforcement learning class and I ask students to make up a reward function for this task, there was always a temptation to put in some knowledge into the reward function. To say, well, we want to reward the agent for increasing its energy, for example. Why don't we do that? Or we want to reward the agent based on how far it is currently from the goal, right? The closer you are to the goal, maybe the more reward you should get. And those are very good thoughts, but in some sense, if you look at this formulation, oftentimes we actually resist the temptation to put in too much knowledge into the reward function. That's partly because, we say the reward, but then the agent optimizing this return accumulates the reward. And so even if you're thinking of a reward that per time step gives the agent a lot of information, the cumulant of that may actually be not what you intend, right? And so oftentimes you will see the situation where the reward, the immediate reward, is very much not informative, okay? It's very vanilla. It just has to capture the task. And then the agent can still learn, in this case, very successfully. This is an easy problem for modern reinforcement learning agents. So the agent can still learn to optimize the right thing. The other sort of interesting aspect in this problem is that, of course, there will be many reward functions that all lead to the same final policy, right? I can give -1 per time step. I can give -10 per time step, right? So in some sense, the actual magnitude of the rewards doesn't matter, right? What we're after is a policy. And so, there is a step in which we decide the reward function. I'm going to assume that this is given, okay? And I'll talk a little bit tomorrow about extensions of what happens if we don't actually really know entirely the reward function. Okay, so now let's look also at an example of a continuing task. So what is the continuing task like? Here we don't have natural episodes, but just the agent just goes on and on. And so for continuing tasks, we often will have this notion of return where the future rewards get multiplied by a constant gamma, which is called the discount rate or the discount factor. And it's something between 0 and 1. And so, one way you think about gamma is that it's telling the agent over what time horizon it should focus. So if I set gamma equal to 0 here, the agent's return is just the immediate reward. And so I will end up with essentially what's called a bandit problem, where the agent only focuses on optimizing the reward that's happening immediately after the action. If we make gamma very, very high, close to 1, then the agent is going to care a lot about rewards that are received farther into the future. And there is sort of a natural time horizon, right? Because at some point, gamma to the k will become very small, and rewards afterwards essentially don't matter. So gamma, in some sense, defines the time horizon that the agent cares about. So let's look at the problem that is that can be solved as a continuing task problem. So this is again a simple dynamical system that's called pole balancing. And by the way, if you want to play with any of these environments, they're all available in the Gym suite from OpenAI, and so you can try them and try reinforcement learning agents on them. So in this case, we have a little cart. There's a pole that's on top of the cart. And the agent can act on the cart, so it can push the cart sideways. And its goal is to maintain the pole as upright as possible. So if the pole falls beyond a certain angle, then the episode has failed. And the track has some limits, so the agent can't go beyond the length of the track. So this is, we can think of it as a maintenance task. It's not a goal-based task. It's not like the agent is trying to get somewhere, like in the mountain car. It's actually the agent trying to maintain the system in a good state. And in this case, we can actually phrase this task both as an episodic task as well as a continuing task. So as an episodic task, we can say we're rewarding the agent some amount, +1, for every time step before it fails. And so every time step that you're still alive, you get a +1. And the return is just the number of time steps before failure. Now, of course, ideally, we'd have an agent that never fails. And so this means that this sum is just going to grow and grow and grow. And as a result, maybe we have a problem over time as the agents get really good, that the sum gets bigger and bigger, and maybe we run into numerical issues with our algorithm. The continuing task formulation says the reward will be -1 upon failure. Otherwise, we get no rewards. But we're going to use discounting. So there's going to be a gamma. And so whenever, if you fail very late, then actually your return will still be kind of close to 0, just ever so slightly negative. And so this captures this notion that the agent could possibly go on forever. And it's still always going to be better not to fail, right? Always get the 0 rewards than to fail. So I'm going to stop here for a minute and see if there are any questions or comments so far.
Yeah, if you have any question, please raise your hand. Perhaps I could start with one, Doina. So do you ever do, let's say, no discount in infinite horizon?
No, because things can get very strange. The cases where we have no discount are typically cases where we know the task will end somehow, right? So even if we have a game that in principle could go on forever, in practice, we are going to have a finite number of time steps that we allow with the agent, right? 5,000, 10,000, whatever it is, however patient we are. And so in that case, we might say, there's no discounting and we're just looking at the total reward. But in tasks where there's a chance of the episode going on forever, if we don't use discounting, it is possible that we're going to obtain divergence, right? The sums of rewards need to otherwise be guaranteed to be finite. Now, there may be other ways to guarantee that the cumulative reward or that the return is finite, then we don't have the need for discounting.
Thanks. So I think we don't have a question at this moment.
Okay. So let's now talk about value functions. So we defined returns, and we saw that returns are the quantity that captures the agent's success at solving a task. Now we're going to want to estimate the expected return. Okay, so this is the first thing that I'm going to say. Reinforcement learning, in the way that I'm going to talk about it, is about expectations of returns. And for example, we're not going to very much take into account things like variance or other things like that, right? And maybe one can view this as a limitation, but actually we can go really, really far with estimating expected returns. There are two problems that we're going to look at. The first one is prediction. So this means the agent has some current way to behave, some policy pi, which is fixed and given to it. Okay, maybe it's uniformly random, so that it doesn't have to be a good policy. It's just some way of behaving. And the prediction task is about estimating the expected return. The other task that we're going to talk about is control. This means how do we find a good policy? So whenever you see a star, that means optimal, okay? Optimal with respect to the return optimization criterion. So in the control case, we would like to find the optimal policy. And to do this, we're going to define some mathematical objects, which are called value functions, and we're going to define them actually on the next slide. Whenever you see them in these small letters, these are ideal values, right? The exact expected values. But really, during the algorithms, we're going to use estimates for these value functions. So whenever you see a big V or a big Q, this is an estimate, and it's capitalized because it's a random value. It depends on the experience that the agent has gathered so far. Okay. So now, how do we define value functions? So here's the definition for the state value of some policy, okay? It's the expected value of the return, GT, given the state in which the agent starts. So the value function is going to map states into numbers, right? And for any particular state S, V pi of S, the value for the state under policy pi, is the expected return that we would get if we start in S, and then all the subsequent actions are drawn from the probability distribution given by pi. Pi is given, so that's it. And here we are just expanding it a little bit to show the continuing, the continuing task, the discounted case. But any kind of definition of return that you want, you plug it in here, and we're going to estimate this expectation. And similarly, of course, we can estimate here action value functions. Now, what does this mean? This means that the agent starts in some state, and on the very first time step, it's allowed to do something different from the usual, okay? It's actually allowed to take an action A that might not be drawn from policy pi, but is some deviation from its current policy. And so these action value functions will be very useful in terms of allowing the agent to experiment perhaps with things that it has not seen before. So now, what does this value function look like in an algorithm? It's going to be some kind of function approximation box where we're going to have some parameters in this box. the box takes in a state as an input, and then at the output, we're going to compute an estimate of the value function. So v hat here is the estimate of the value function. And in this case, we have a box that's parameterized, so maybe it's a deep neural network. And we're going to have to update it. So the algorithms, the value-based reinforcement learning algorithms, are all about this target. Okay, how do we compute the target that we use to update this box? And the most natural thing to do if you're coming from a supervised learning background is to say, we're going to run our policy, okay? And we're going to try and get estimates of this true expectation v pi of s, okay? And those will become targets. And now we have essentially a regression problem, okay? So the agent does trajectories, it sees states, it gets returns, and sampled returns. And we're going to run a regression from the state to the return. And here, mu of s, so this probability measure here is just a fraction of time that we spend in state s. So if a state is something that the agent encounters a lot, obviously it's more important and we would like to really pay attention to it. And so we can now do stochastic gradient descent, right, to take this error objective and to turn it into an algorithm. And I just wanted to show you sort of this picture here because it's going to be a little bit useful to relate the algorithms to each other. The agent is at some state here, st. It has a policy. So this policy is going to take action. So these little black dots here are action choices. So at a state, the agent has a policy, it's drawn a sampled action from this policy, right? So it's following this red path. Then there's a distribution of next states that it could encounter, and that's the environment, okay? And so here the environment has given the agent a next state. The agent is querying its policy again at this black dot, draws an action, moves to the next state, and so on, up until the end of an episode. Now that we've observed the whole red trajectory, we know the returns for all of the states that have happened on this trajectory, okay? And so now we can essentially do something that is like supervised learning, take all this data, pair of state and the return from that state, put it all in a bag, and then do gradient descent. And so you obtain this kind of update rule here, right, where you want the value of a state to become similar to the return that's been observed from that state. And so GT is the desired value, V of ST is our current estimate, and we use a learning rate. Of course, if we have a function approximator, this is our error that we're going to use, and we're just going to use backprop or whatever optimizer we have with this particular error in order to update the value function. And so this is going to allow us now to update values. And so this is just a picture taken straight out of the Sutton and Bartow book, just to make this algorithm a little bit more concrete. We won't look at a lot of these algorithms, but just a couple to give you a more concrete sense of them. So you consider the policy to be an input. You have some differentiable function approximator v hat. We're going to initialize its parameters to something, say 0 or something small and random. We're going to then generate episodes by drawing actions according to policy pi and update the parameters. Okay, so this is just vanilla gradient descent. Vanilla, except for one thing, right, which I just want you to keep in mind, which is that these inputs, these states ST, are actually not IID, right? They are drawn sequentially from a trial. And so that can become a problem if what we're doing is nonlinear function approximation. And there's various usual ways to deal with this problem. For example, take the data from many trajectories, chop it up, and then make a replay buffer and resample states from that. So that's going to be a standard trick that we're going to see in several of these algorithms. And now I want to just sort of show you a little example of sort of what does this look like, right? So this is a very simple task, which is a random walk task. The agent walks along this x-axis. On one end of the axis, it gets a -1, and the other end of the axis it gets a +1. Red here is the true value function, right, which is linear in this case, v pi, for walking uniformly randomly in this environment. And the blue line here is a Monte Carlo estimate that's obtained by a very simple function approximator called a state aggregator. So, excuse me. So a state aggregator does nothing but partition the state space into chunks, right? You can think of clustering or any kind of discretization as a state aggregator. And so what can we see in this picture? So first of all, we see that we are getting an estimate of the value function that is pretty good, right? This blue line is hugging the red line. So that's encouraging. We also see, however, that there is a bias, right? So the blue line is never going to be identical to the red line because we've chosen a discretization, and now the best we can do is assign a single value to all the states that are in one of these partitions, right? And so that kind of bias that comes from the function approximator is going to stay with the algorithm, and it's going to become a little bit of a problem later on, okay? Of course, if I have a very flexible function approximator, so not a discretization, but maybe I have a deep net or something like this that has a very high capacity, then in principle, I can estimate this line very, very closely. And so again, this problem is essentially like regression, except for the non-IID inputs and the non-IID targets, right? Because the returns also overlap, and so they will also be non-IID. Now, so far, I've made no assumptions really about the environment of the agent, right? I have some way of dealing with this problem that is assumption-free. But if we know something a little bit more about the environment of the agent, then we can actually build algorithms that are a little bit more powerful. So the first assumption that one can make is a Markov assumption, okay? What does this mean? We can assume that the next state and the next reward of the agent only depend on the current state and action and not on anything that has happened before. So this turns an arbitrary environment into an environment that's called a Markov decision process, right? So this is a Markov decision process. Think of it as a Markov chain, but where you also have actions. And so the agent has choices. But other than that, the Markovian property is the same. So what does this mean? This means that now I can think of structure in the environment, which we may be able to exploit in order to build algorithms. So here's a kind of structure in the form of the transition probability distribution, which says, if I'm at state S and action A, then the probability distribution over the next state S prime and the next reward R, is well-defined and only depends on SNA, nothing that has happened before, okay? And I can further break this up if we want into a transition model, which is P of S prime given SNA, sometimes also called the dynamics of the environment, and the reward. And the reward is just the expected value of the immediate reward that we would get on the next time step starting at SNA. And so these two quantities, P and R here, form what's called the model of the environment. And you can think of these as going jointly, right? And then you can think of them as sort of being independent of each other. So if we have a Markov decision process, then we should be able to exploit this conditional independence in order to get algorithms that are somehow more efficient, okay? And not only that, but the problem of optimization becomes actually a bit better defined, okay? So in particular, if we have a Markov decision process that is finite, there's beautiful theory that comes from the days of Bellman that says we can have partial ordering over policies. And if policies are partially ordered, we can also show that there is actually an optimal value function and a corresponding, at least one corresponding optimal policy, which is deterministic. So this is theory that's coming from dynamic programming. In our case, when we have discounting, part of the way that we can justify these statements here is because the discount factor leads to a contraction in value space. And so a lot of the proofs that you see rely on these contraction arguments in order to show the uniqueness of these fixed points, and also in order to show then that if we have estimates that they are converging to these fixed points. So we're going to have some optimal value functions, optimal state value functions, and state action value functions. the way that we think about these is that they're just maximizing over the space of policies. Now, why is this important? If we have the optimal action value function, then essentially getting the optimal policy is a single step, okay? So we take Q star, which is the optimal action value function. We take a max over the actions, and that immediately gives us the optimal policy. Now, this kind of sounds a little bit magic, right? Because we're obtaining an optimal for a long-term quantity by looking at something that looks like a one-step quantity. But really, Q star, remember, is an estimate of long-term return. And so Q star is a long-term quantity in here. Okay, so now let's look at Bellman equations. Okay, so Bellman equations are recursive equations that we can use in order to estimate value functions. And so here we have the basic idea of taking this return and breaking it up into two parts, right? So the typical dynamic programming thing. The first part is just the immediate reward, and the next part is the long-term return with the discount factor, right? So this equation just says the return at time step t has the first reward and then the rest of the return from time step t plus 1 onwards. And so when we write the definition of v pi, of the value function, we can actually write this definition using this formula here. And of course, we notice that the expected value of gt plus 1 is just the value function from state t plus 1 onward, okay? And if we have Markovian structure that is being assumed, then we can further break this expectation up, okay, into its various parts, okay? And so we obtain the Bellman equation on the bottom that says the value at state S is an average of targets, okay? These targets are reward plus the value of the next state, discounted. And the averaging is happening according to the probability distribution of the policy pi, which is under the control of the agent, and according to the probability distribution of the environment. And so, of course, now we, if we looked at this, and we imagine that this is a discrete environment, this is just a linear system of equations. In principle, we could solve it. The devil is in the details, right? So typically, we don't have just a discrete, small enough system. We have a continuous system, like in the case of the examples that we've seen, or we might have something like Go, which is like 10 to the power 30 states. So we're never really going to be able to solve this as a linear system. We're going to need some approximation methods. But it's interesting to think for a minute about the structure of this problem, right? And what does it look like from the point of view of the agent, right? So consider again this agent and its tree of possible trajectories, right? And so the agent is at state st here. And the dynamic programming approach will basically say the agent should consider all of the possible actions that it has, right? This is according to pi. The agent considers all of the possible transitions to next states. This is what P here, the model of the environment, is doing. And then we're going to construct, from here on, we have some value, right? So this is the value of these white circles here, the value of the next state. And we've accumulated some reward on this little jump, right, from ST to the next state. And so that's the reward R. And we're constructing the targets based on this breadth first, like look ahead, one step wide look ahead. So this is interesting, okay? It gives the agent one time step, right? One transition in some sense over which to think about stuff, but it considers a very big expectation. And these sums essentially in practical applications can't really be carried out, right? And in some cases, of course, they would become integrals because we have continuous states here. So, revisiting Monte Carlo, right? Monte Carlo is basically a depth first like approach where the agent takes trajectories, takes paths through this infinite tree of possibilities and updates based on these sampled paths, okay? And then dynamic programming takes this breadth first approach where it's looking at all the possible choices that one could have. What if we tried to take the best of both worlds and did a one-step sample, okay? So that is the simplest temporal difference learning method. And it's one of the very key ideas in reinforcement learning that's really at the core of many of the reinforcement learning algorithms, okay? So the idea is the agent is at some state st, okay? It takes one action, it observes its reward, and it arrives at a new state st plus 1. And then it considers from then on what would happen as being summarized in its current value v. Okay, so v of st plus 1 summarizes everything that would happen from st plus 1 onwards. And so like in Monte Carlo, we're going to take one transition, not consider the full expectation. So one way to think about this is if we had the dynamic program here and we sampled the action and we sampled the transition, right? It's a sample of this dynamic program. Of course, the challenge now is that this target that we're using is not perfect, okay? And so in TD, in fact, we're going to have this target v of st plus 1 that's going to be just according to the agent's current parameter estimates. And the only way that we can hope this is going to work is that over time, these targets would become better and better. And so maybe over time, this reward plus value of the next state will in fact become closer to what the dynamic programming target would be. And so taking these samples is not going to be too bad. So this is the basic idea of temporal difference learning. This is a class of methods whose intuition is due to Rich Sutton back in 1988 and also worked jointly with Andy Barto over some period of time. And this kind of reasoning, time step to time step, is going to be the crucial building block also in algorithms like SARSA and Q-learning for control that we're going to talk about next. So just to revisit this a little bit compared to Monte Carlo, in Monte Carlo, we have a target that's the actual return of the agent after time step t. In temporal difference learning, the simplest method, which is this one-step method called TD-0, the target is the reward that the agent gets plus gamma times the value of the next state, okay? And one can think of this again as an estimate of the return, where we've taken the first reward and we've replaced the entire tail of the return with this current guess v of st plus 1. So like dynamic programming, this algorithm bootstraps. It uses the agent's current guesses in forming targets. But like Monte Carlo, it samples. Okay, and it's really like at the intersection of these two approaches. Now, from a sort of mechanistic point of view, how would we implement this in a network? This actually looks perfectly fine, right? We have a loss function here, which is this difference between our estimate at the next time step and our estimate at the current step, v of st. This is just an error signal that we can feed to an algorithm, a net optimizer or a linear function approximation optimizer. From the point of view of theoretical analysis, this is actually now quite tricky because v, this quantity here, is depending on the agent's current parameters. So this is no longer a stationary target. Actually, it moves all the time as the agent learns, right? And so from a theoretical point of view, these algorithms are in quite a different category. We're going to talk a little bit about how to think about these algorithms in a minute. So just to give you a little bit more sort of intuition about temporal difference learning compared to Monte Carlo and what their guesses would be, okay? Imagine that you see this set of data, okay, where you have state A followed by a 0, state B followed by a 0, okay? And then for a bunch of times, 6 times here, you see state B followed by a 1, and then there's a B followed by a 0, okay? And so you're asking what's the value of state B and what's the value of state A? So if we're thinking of doing Monte Carlo here, Monte Carlo would basically say, take all of the estimates of B returns that you've seen, and that's their average is the value associated with B. So the value of B in this case is going to be 6 on 8, right? Because we've seen 6 ones out of 8 tries. What's the value of A? Well, Monte Carlo will say A has only seen a 0, right? A 0 return, 0 plus 0 here. So the value of A, based on returns, should be 0. So that is the squared error minimizing solution, right? We're using the averages of the obtained data. Now, what does temporal difference learning do? Temporal difference learning is going to say, I actually saw a trajectory where A got a 0, but then it led to B, okay? And from B, we're going to have some value, and actually that's what I want to associate A with, right? So temporal difference learning really wants to maintain this time consistency of these guesses with respect to thinking of the agent actually being in a Markov decision process. And so one way to think about what temporal difference learning would do is that it would take this data and build a model, a maximum likelihood model out of this data of the transitions that the agent is experiencing. And so based on this model, B sometimes goes to a terminal state with a reward of 1 and sometimes goes to a terminal state of a reward of 0. And A transitions to B, okay? So the value of A is gonna be 0 plus gamma times the value of B. And so in this case, even though we have only seen one trajectory where the return of A is 0, the agent will assume that the value of A is actually 0 plus gamma times 6 on A. Okay. And so this is an important sort of consideration and distinction between these two algorithms. Monte Carlo is a gradient-based algorithm that considers as its loss function this weighted mean squared error, weighted by the state visitation density, whereas temporal difference learning from a conceptual point of view is as if you took the data, fit a Markov model to the data, and then the value function is approximating the value that would be computed from this model, okay? Now, what does this mean? This means we're introducing now an assumption, right, which is going to bias our estimates. If this assumption is true, then it's great, right? We're doing this in the service of reducing variance, right? It's the kind of bias variance trade-off that you have in supervised learning as well. And so if the Markovian assumption holds, then this is actually a great thing to do. If the Markovian assumption does not hold, then the agent using TD is going to end up with some biased estimates, right? And that may or may not be a problem. Oftentimes in practice, it is not a problem, but from a theoretical point of view, it can complicate things quite a bit. And so I want to sort of show you what this bias looks like in this very simple setting, right? So this is the task that we looked at in the context of Monte Carlo. It's a random walk task, and this red line is the true value function. If you recall, Monte Carlo had this blue line that was really hugging the red line. Okay. TD also has a zigzag blue line, and it's actually also pretty good, but you can see that it's not really hugging the red line. Actually, it has some further bias here, especially observable at the edges, right? So it's lower here, it's higher here, okay? Now, why is this? Well, in this case, we've aggregated states, and TD, in this case, essentially is trying to say from one partition to another partition, I have a Markov transition. But this is not entirely accurate because the Markovian level is between states, okay? It's not between the partitions. Between the partitions, actually, where you end up does depend on exactly which state you were in this previous partition, and that's not something that's part of your state. And so the Markovian assumption, whenever you're doing function approximation, is going to be violated a little bit, okay? And we may want to have some algorithms that don't fully rely on the Markovian assumption, but that actually are sort of a little bit robust with respect to that. So let's look at what that might look like, okay? This is what people sometimes call n-step TD, right, or n-step prediction. And we're gonna look at sort of two versions of this. N-step TD basically says, instead of deciding that we're only gonna look at one step, state, reward, next state, maybe we want to look at two steps, a two-step little trajectory, squiggle through the tree of trajectories. Maybe we want to look at 3 steps, right? If we looked at all the steps until the end, that would be Monte Carlo, right? And so Monte Carlo is this algorithm that does not make any Markovian assumption at all. TD-0, which we have here, has a full-blown Markovian assumption, right? And so these intermediate steps where we decide to look sort of a bit further or a bit less into the future, in some sense use n, the number of steps, as a trade-off between how much we rely or not on the Markovian assumption. And this trade-off is made through how much we're emphasizing our current value estimates, right? So in Monte Carlo, the agent's current value estimates are not really part of the targets at all. It's all return, right? It's all real data. In TD, we take the agent's value estimate after one time step, and so it's discounted by gamma, but it's still very present in the targets. The discount for a two-step TD algorithm would be gamma squared. So the guess that the agent has gets washed out more because it's multiplied by gamma squared. If I have an n-step TD algorithm, the agent's current guess is actually discounted by gamma to the n. So if gamma is less than 1, right, and if n is sufficiently large, the agent's current guess is going to be discounted quite a bit. And so the agent essentially can use this as a knob to trade off between using or not using the Markovian assumption, and essentially that is going to lead to a bias variance trade-off. And very often in algorithms, we see that intermediate values here are really best. And so from the point of view of the mathematics of these n-step targets, we simply use truncation after a different amount of time, right? So the agent is still taking one trajectory to the tree, but it will take the rewards along 2 time steps or n time steps, and only then consider its current guess about the value function as part of the target. And because of this, because we have this gamma raised to a power here, the accuracy of this target matters less, right? And the agent becomes more robust. Now, this n is now a parameter, and it's a little bit awkward to work with it. It's become much more popular with deep RL algorithms because we can just go for a while, right, and then sort of take these returns and chop them up and put them in the replay buffer. But there's other sort of more graceful ways of interpolating between these, and so one of them is this lambda return. The lambda return is an exponential weighting here it's a weighting between each of these returns, okay? And so we can play now around with a parameter that's between 0 and 1. 1 means you're doing fully Monte Carlo. 0 means just TD0. And so we can do the bias virus trade-off in this way. And so just from a point of view of thinking of all these algorithms kind of together, okay, we have dynamic programming, which is fully bootstrapping, okay. We have Monte Carlo, which is fully looking on trajectories and sampling. Then we have TD, right? So TD is this algorithm that looks just at one step, and n-step TD is on this vertical axis, interpolating between temporal difference learning and Monte Carlo. And then, of course, we can consider other things like, for example, the width of the backup. Like, do we consider multiple actions at a time step? And that would interpolate between TD and, let's say, dynamic programming. And just for context, of course, there's also exhaustive search, right? So if you have an environment that lends itself to exhaustive search, you can do something like that. But, of course, our environments typically are too big for that approach. So I will pause here for a minute and see if there are questions.
Good. So I think we have a couple of questions. Mm-hmm. So first, we will, I think there's a question from very early on. So from Martin, says, basically asking, is discounting a way of putting intelligence into, say, optimization to help optimization? So I think the question is asking, how does the discount affects the optimization process?
Yes, so that's a great question. And actually, there is some beautiful work by Nanjiang and colleagues from a few years ago that looked at the role of discounting in terms of controlling the complexity of the policy space of the agent. And so, one way to think about it is if the discount factor is 0, then the agent, it's like I said, it's basically a bandit. So the long-term consequences of actions don't matter. We only look at the immediate reward. And so in some sense, that's an easier task. And you can expect that an easier policy is able to obtain good results there. The longer the discount factor, the more we have to take into account the impact of the actions. And so, even if in the long run, we would like the agent to consider a very long time horizon, if the agent doesn't have very much data, then it can be beneficial to make that discount factor a little bit shorter in order to give the agent an easier time. And the intuition of their analysis, at least, is that if the agent doesn't have very much data, then if it fits a model, like a Markovian model, let's say, that model will be flawed. And when you're doing many dynamic programming backups with that model, it's not going to give you very good solutions. And so even if you're, in principle, you could learn a very complicated policy. In fact, you're going to learn a policy that's pretty bad because the errors in the model compound and the discount factor doesn't do anything for that. Now, there's various works that look at the temporal scale at which an agent should reason about the world. And so I'm going to tell a little bit more about that also tomorrow.
Mm-hmm. So the second question, Remy asks, so are reinforcement learning algorithms actually good at learning in the sense that we've seen like amazing stuff like AlphaGo, but they took a lot of like trials and errors that we humans cannot afford. So perhaps the question is asking, how about the sample efficiency versus a human? Is there a good way to evaluate that other than the current way we're evaluating?
Yes, so I think the sample efficiency of RL algorithms remains high in many cases. Now, why is that? Well, on one hand, the agent needs to gather its own data, right? So the agent might need a lot of time steps to see anything interesting in the environment. A typical example is this Montezuma's Revenge game in the Atari suite, where the agent is wandering around in the environment, and it's only at the very end of the game, like when you won the game, you actually observe the reward, and that's it. Otherwise, there's no rewards along the way. So it can take an agent, a very, very long time to, by chance, kind of stumble onto the throne room, or it may not ever do that. So exploration is difficult, and the data that the agent is seeing is really crucial in driving its learning. And so from that point of view, yes, it's hard. At the same time, we are making a lot of progress understanding the issues surrounding sample complexity. And Montezuma's Revenge is solved in the latest incarnation of Agent 57. So progress has been made. The sample complexity still needs to decrease further. And I feel that for that, we need to find ways to leverage more of the agent's experience. So again, I'll talk about this a little bit tomorrow. But when a human is playing the game, even if the reward hasn't happened yet, as you're seeing transitions, you're learning about the structure of the environment. Maybe you're making an approximate model of the environment. Maybe you are noticing some things and you are remembering where they are, so that maybe you will now have a policy that brings you back. Let's say you've noticed that there's a key somewhere, there's a policy that remembers how to bring you back to that key. And so trying to leverage the agent's experience, not just to learn about the single reward, but to learn about many other things is important. And so there's certain approaches that have been used, for example, auxiliary tasks, Unreal, and so on, that are trying to get at that. I still think that we need to make a lot of progress in terms of the sample efficiency of reinforcement learning. Now, this being said, of course, the sample efficiency is not great for other kinds of algorithms either, right? So deep learning algorithms tend to require lots of samples, right? Or tend to require us knowing something about the structure of the data in order to build good architectures. And so in some sense, what we're seeing with RL is also a reflection of the perhaps sample inefficiency of deep learning methods more generally.
Mm-hmm. So perhaps we take one more question during this round. So, here's a really good one. I like it. Is there a link between the n-step TD and model predictive control, like the stuffing control?
that's a great question. So
that's from Pierre. Yeah.
So there's so model predictive control, just for those who don't know, is an approach in control theory that has to do with having some model of the environment that we're going to roll forward for a few steps. And then we're going to observe what happens after those few steps. We take that trajectory, and now we decide based on its outcome what to do. And we're going to take one action and then do this again. So there is indeed a common flavor, right, to model predictive control, in the sense that in n-step TD, the agent also takes n steps forward, and then the value function that it has, in some sense, it's this sort of reading on the actual environment. Now, in model predictive control, typically we take these steps using some kind of model that's in the agent's head. It's oftentimes a simplified model, maybe it's a quadratic model or something like this. In TD, we really take the steps typically in the environment. Then we observe what happens, we take this target and we propagate it back. So the second aspect that does not always happen in model predictive control is this taking the credit from the target and propagating it back to the first state where we've chosen an action. In model predictive control, we take the data and we're going to update our models with the data, but there's not directly a credit assignment in terms of a value function. We don't have a need for a value function because we just do these kinds of rollouts. I think this points to a more interesting sort of relationship between model predictive control and, let's say, model-based reinforcement learning, more broadly speaking, like the use of models to update value functions. And so both are model-based, but if we consider the use of models, it's a little bit different, right? So in an RL task, if I build a model, I will typically use that model, again, in order to update the value function, in order to do approximate dynamic programming backups, for example. Whereas in model predictive control, we use the model in the service of choosing the next action, but not necessarily to do this kind of credit assignment. And these two are very different uses. And in particular, maybe a model that is quite imperfect is still helpful for this problem of choosing what to do next, but might be very detrimental if I use it for credit assignment. And I think there's actually quite an interesting, perhaps, space of thinking that needs to happen between these sort of two uses of models. And I think because both use the word model, it's a little bit overloaded. But it would be interesting to think further of the lessons that we can take, let's say, from model predictive control, which empirically tends to work in quite interesting ways, as Ben Recht and other people pointing out, and take those lessons and apply them into model-based development.
Yep, that's a great answer. Maybe we can chat after about this. Okay, so I think we have more questions, but we're gonna first let Doina resume the lecture and ask the question later.
Okay, so let's talk then a little bit about doing TD with function approximation. Okay, so what does this mean? It means we're going to have, again, a function approximator. The state comes in, v hat comes out. We're going to have a target. The target's going to depend on the agent's behavior. And so this target in temporal difference learning is going to come from TD learning, okay? And so the updates that we're going to do are going to kind of look like gradient descent updates, but be slightly different, okay? This is the case that the RL book by Sutton and Bartow calls a semi-gradient update, okay? What does this mean? It means we're thinking of the target. We're pretending that the target is independent of the agent's parameters, right? And the only thing that depends on the agent's parameter is this v hat of st, so the agent's value estimate at time step t. And so we're going to take a gradient with respect to the parameters here, but pretends that the target is fixed. Now we know this is not true. We know that the target contains v hat in it, v hat of st plus 1. And so this algorithm, in some sense, is a little bit strange. So we're going to want to see sort of what's the justification for doing this, and how do we think about this algorithm from a bit of theoretical point of view. Okay? And again, just for concreteness, here's the algorithm. Okay, this is temporal difference learning, TD0, not n-step. but with function approximation. So we're going to have a function approximated parameterized by theta. We choose actions according to pi. We observe rewards. We observe next states. We make a target, which is reward plus gamma times the value of the next state. But then when we do an update, we pretend that this target is really fixed, and we take a gradient of v hat of s only. Okay. And again, we can, of course, do n step here. So in that case, instead of having this one step r plus gamma v hat of s prime, we would have an n step target. It's very easy to do that. And we can also take data and put it in a bag and aggregate it and then do updates from the bag. Okay. Now, how do we think about this algorithm from a theoretical point of view? I'm going to explain the intuition in the linear case, okay, because that's just simpler. So imagine that the agent's parameterization for this V is linear. Okay, so in this case, for example, the agent has two parameters, theta 1 and theta 2. And so all of the value functions v theta here that the agent can represent live in this plane. Okay. What does TD do? Well, TD, we discussed, is using the Markov assumption, and it's essentially trying to approximate what would be a dynamic programming update. So one way to think about it is that I have an operator that can take a vector here, any value function, and sort of feed it through the transition of the environment, the model of the transition of the environment P here, and do a translation according to R, the reward vector. And that's going to give us a next estimate. So from a v theta here, I'm going to get to a value function here that's v pi v theta. Okay, that would be the one-step dynamic programming. And TD does exactly this, but it does it sort of in a sampled way. Okay. Now, this value function, b pi v theta, is not representable by the agent. And so the agent is going to need to bring this back, okay? So there's going to be a projection operator that happens here that brings this one-step Bellman updated value function back into this space of value functions that's actually representable by the agent, which is the plane. And so now we can iterate this process. Okay? So TD, in expectation, iterates this process of starting with some guess of the value function and then doing these steps of doing a Bellman backup and projecting back down, doing a Bellman backup and projecting back down. And so the agent is going to continue sort of doing these zigzags. Until when are we going to do this? Well, if the agent were free to do what it wants, there's some true value function v pi that's associated with policy pi that the agent wants to get to. And this update process is going to sort of meander around here, going towards this point where we're going to take v pi and project it down to the space of parameters that we have. Okay. And if we are at this point, right, where we are, v pi gets projected back down on the space of parameters, at this point, nothing will change anymore. Okay, and our agent has converged to the best that it can possibly do. And so this is what TD algorithms are going to try to do. They're computing essentially a fixed point update. It's not a gradient-based update. And even though it looks kind of like a gradient, but TD is really not a gradient. It's a fixed point update of this type where we're doing an operator, a Bellman operator on the value function, and then a projection operator. And this projection is going to depend on the distribution of states that the agent is visiting, which is according to pi. It's, of course, going to depend on the parameterization of the value function. Now, this is the linear case. And so in the linear case, one can clearly see that eventually we will converge to this point, right, where the agent has the best sort of possible projection of the true value function. It's obviously not going to have the exact value function because that's not representable. Now, you know, what this also means is that gradient-based considerations don't apply, okay? And so even though in practice we use, let's say, second-order methods, optimizers, Adam, whatnot, that are conceived for gradient descent, we sort of take that with a big grain of salt because this algorithm is really not a gradient descent algorithm. So in terms of convergence, when we talk about the convergence of TD learning, we talk about this from a fixed point analysis. And so the idea is if we consider the agent's trajectory through the environment, the agent is going through some feature vectors phi. Excuse me. And we can consider an approximate model of the environment, okay, where we have transitions from feature vector to feature vector. That's this matrix A. We can also consider an approximate reward model where rewards are averaged according to phi. And now the solution that TD is computing is going to be, roughly speaking, A inverse B. Okay, so the model matrix inverted times the reward vector. And so TD typically can be seen as converging to this kind of solution. And if we're looking at the value error, okay, so this vertical segment here, okay, between the value and the true value, that's going to be somewhere in a ball around the solution that would be obtained by Monte Carlo, right? So minimizing the squared value error is what Monte Carlo would do, is this term here. And we're going to be somewhere in a ball, and the width of that ball is actually controlled by gamma. Okay? And so we're not converging to the Monte Carlo solution. We're converging to something that is close to the Monte Carlo solution, but possibly quite, a little bit biased. Why is this a reasonable place to converge to? Well, it's because in some sense it's very natural, right? What's the best you can possibly do? If you have a plane and you have some point out here, right? Project the point to the plane. That's the natural thing that you would want to do, right? What happens in the case of nonlinear function approximation? That is a very interesting open question. There are some attempts at theoretical analysis, but intuitively what happens with nonlinear function approximation is that we don't have a plane here. We're going to have a manifold, right? And so at the very least, we can't really talk about linear projections, right? We'll need to talk about what happens to the curvature of that manifold. So that complicates things a bit. The other kind of complication, of course, is that in general, we're not going to have a fixed policy, but the policy will be changing. And so even if we're in this plane case, when the policy changes, the plane will tilt. And so the analysis is going to become quite a bit harder if we're considering variations in this plane. And essentially, a lot of the theoretical results assume that from one policy to the next policy, this variation is going to be very, very small, right? And so the plane tilts only a little bit. So I think that I would like to stop there, and just to sum up sort of these ideas around policy evaluation. We have now value function approximation that is enabling RL to scale to larger state spaces. Unfortunately, I didn't get to talk about control, but I really wanted to tell you a little bit about the theory, just so we put a little bit in perspective the ideas of control, and I'm going to start with that tomorrow. So intuitively, what we're going to want to do next is to take the value functions and use them to drive the choices of policy and the improvements in policy. The other thing that I want to mention is that, again, you have to remember that TD is not true gradient descent. And so this complicates the theoretical analysis, also makes it a lot more interesting, my personal point of view there. But in the linear on policy case, so that means we're getting samples from the policy that we're interested in, this is still guaranteed to converge to this kind of projected solution. And learning is typically much faster. And this really boils down to a bias variance kind of trade-off, right? So we're putting it bias by using the Markovian assumption. We're trading off against variance, and that can be quite beneficial. And you can actually kind of see this here. So these are just some sample results where we have Monte Carlo is up here. Okay, these are error graphs, so low is good. So Monte Carlo has pretty terrible error in this case after a finite number of samples. This is TD0 here. TD0 is better, but because of the bias, we still have some error. And then we're looking at some of these lambda return kind of methods in between, and you can see that these can be a lot better, right? And essentially it's because they're trading off bias and variance in a good way. Are there any further questions?
We had a question early on, and let me just get this one. And meanwhile, if anybody has any question, perhaps Doina can still take one or two before the end. So previously we had a question about the sample efficiency. So is there a way we could use causality to improve sample efficiency?
I certainly hope so. This is part of my hope. So intuitively, if we were able to build a causal model of the environment in an efficient way, then in reinforcement learning, the model should be a causal model. And if the agent focuses on having a causal model, then from the point of view of understanding the impact of decisions, that would be amazing, right? And we don't have to sort of spend resources modeling randomness in the environment that doesn't really matter to the agent. Now, the question that I have for you who are perhaps more experts in causal learning is, how can we do this efficiently? And so the part of the difficulty generally with model-based RL is that we have to gather the data, then we can use the data to learn the model, or we can just use the data directly to learn a value function. And if causal learning also is kind of data inefficient or requires a different kind of exploration, there may be a trade-off there. But I really hope that this is part of the answer. Intuitively, to me, it should be.
Mm-hmm. Okay, so there is another question. So, so is it common to see the state value function estimation from pre-existing data?
Yes, there are certainly approaches that do this. And so there's an approach to reinforcement learning called batch reinforcement learning, which basically says we have a set of data. Maybe it's been actually generated somehow from expert trajectories, people playing a game or driving a car or something like this. And so we can take that data and use it to train a value function. We can also use it to train a policy. But then we have to have this data somehow. Very often we still, if we're going to learn how to control an environment, we still want to go beyond that data. So having a batch of data may be sufficient for doing policy evaluation. And if the policy is not the same, like the behavior policy that generated the data is different from the target policy we want to learn about, we can still do things. There's this whole interesting field called off-policy learning that explains how to still leverage data gathered from a different behavior policy. But if we want to do control, then the agent is going to inevitably end up in parts of state space that the data has not covered. And so we still want to do some acting. We want to have an agent that can gather its own data, simply because it's going to otherwise be put in situations that were not anticipated before. And so if we use some data to initialize a VPI, once that VPI is used to get a new policy, we'll still want the agent to get data according to that new policy to understand how to generalize in places where the previous data might not have been.
Mm-hmm. Okay, great. I think that's it for the question. And thanks everybody for tuning in for today's reinforcement learning lecture. Tomorrow will be at the same time. And thank you, Doina. And if you could just stay on for one moment after everybody else leaves. Yeah.
Certainly.
Yeah.
Thank you very much.